Hello, students. In this lecture, we get to talk about my favorite thing to name and draw, which is the cycloalkanes. So, in case you hadn't guessed, we're going to have some cyclic structures here, some ring structures. So, under the word cycloalkane, it says alkanes with closed loops or rings. And how we're going to name those is by throwing in the word cyclo somewhere. All right, so what do these look like and where are the carbons and the hydrogens? Well, with cyclic structures, we will often see them drawn in line bond form like that. And what we're going to do is we're going to assume that you know where the carbons and hydrogens are. So if we go ahead and we draw in all the carbons, we have one at each of the points, just like we did with the straight chain alkanes. And we have to remember that all of our carbons like to have 4 single bonds around them because each single bond is 2 electrons, and 4 times 2 makes 8, and that's the octet, which we all know is a special situation. So if each of our carbons in this ring is bonded to 2 other carbons, and we'll do the top carbon here, you can see that that carbon is bonded to 2 other carbons. Well, that means it wants another 2 single bonds, and so we will draw those up like this. And what is that carbon single bonded to? Well, that is hydrogen. And if you draw a bond up like that, you need to put a hydrogen there if you mean hydrogen. If you just leave it like that, what does that mean? Well, that would mean that you've got another carbon out there if you just leave it as the stick. You're saying to whoever's looking at it that there's a methyl group out there, a CH3. So we don't want to do that. So if we mean there's a hydrogen there, we definitely want to draw the hydrogen in. Ooh, I hear a siren. I hope that person is okay. All right, if we draw all of the hydrogens in, we're going to see that our structure would look like that. But that's pretty crowded there. So we can do a couple of things. We can draw the condensed format, which looks like that. And I want you to remember that a CH2 is going to be exactly the same thing as an H2C. The H2C for chemists is just pointing out that those hydrogens are pointing outside of the ring, not into the ring. But what we generally prefer to draw as chemists is just the line bond structure like that because it's so easy. So there we can see that we have a molecular formula of C6H12. Now, if we take a look at our cyclohexane formula and we compare it to regular old hexane, which is CH3, and then 4 CH2s and a CH3 on the end, so that's the straight chain, we would see that our cyclohexane has 2 fewer hydrogens than our regular old hexane. And that's because you would be connecting the end carbons together. And if you're going to connect your end carbons together, they have to get rid of a hydrogen each in order to bond to somebody else, because carbons aren't going to want to have 5 single bonds. They would be very upset with that situation. So just so we know, our formulas for our cycloalkanes are going to have fewer hydrogens than the straight chains with the same names. Okay, so how do we name these guys? All right, same nomenclature rules are followed that we already learned previously. We've just got to add in cyclo to the parent chain, and then there's some little quirks of naming cycloalkanes, and we'll talk about that. All right, so for this one right here, you can see that we have a methyl group hanging off of a cyclobutane there. So that's a little box, and it has 4 carbons in the cyclic structure. So we've got a methyl cyclobutane. Now what you might want to do is you might want to say 1 methyl cyclobutane, but that's not necessary to have there, because wherever you draw that methyl, that's going to be the first carbon of the cyclic structure. So if you put methyl where it is right now, then carbon 1 would be here, and then you can go either left or down to have carbon number 2. It doesn't matter. I'll go left. 1, 2, 3, 4, like that, because remember, we want the branches to have the lowest number possible. So if you just have 1 branch off your cyclic structure, it has to be attached to carbon number 1 of the cyclic structure. So you don't need to put the 1 in that case. You can if you want, but you don't need to. Okay, so let's take a look at another cyclobutane to the right. So you see we've got 2 branches there, and we're going to have 1,3-dimethyl cyclobutane as the name. Now we want to do 1, 2, 3, 4, or we could do 1, 2, 3, 4, or we could number it 1, 2, 3, 4. But however we number it, we want one of our methyls to start on carbon 1 and the other one to be on carbon 3. We wouldn't want 2,4-dimethyl. So either methyl group can be number 1 and either one can be number 3. All right, so looking at the next one, we have 2 branches off our cyclohexane here. So we have methyl, and here we have a 2 carbon, and that is what? That is ethyl. You can see that down there in the name. So we've got ethyl. Now we could do 1, 2, or we could do 1, 2. So either way, we have a branch off of carbon 1 and a branch off of carbon 2. And IUPAC says if you have the choice, you're going to give the lower number to the branch that's name comes first in the alphabet. So we have E versus M. So we're going to give the number 1 to ethyl and the number 2 to methyl. And you can see that right here. So we have 1 ethyl, 2 methyl, cyclohexane. Now, down below it says if the non-cyclic carbon chain, so that's the straight chain right here, has more carbons than the ring, then the straight chain is named as the parent chain. So that means that the name right here, pentane, that refers to the straight chain right there, that is going to be the parent because it has more carbons than the cyclic structure. So the cyclic structure has how many carbons? 3. It has 3 carbons. It's a cyclopropane. So because the cyclic structure is considered a branch, we need to take the ane off the end and add YL. So cyclopropane becomes cyclopropyl with a YL on the end, just like methane became methyl and ethane became ethyl. So we have a cyclopropyl, and it's on the end carbon. So we could call that 1-cyclopropyl pentane or cyclopropyl pentane, but here we're being more precise and we're saying we've got a 1-cyclopropyl pentane. We're not going to call this pentyl cyclopropane Because the pentane portion, is larger than the cyclopropyl portion. All right? So let's do some problems. Let's name these compounds. Okay, so with the first one, we're going to take a look at it and say, alrighty, which is bigger, the straight chain or the cyclic structure? And for most of us, we can see right away that the cyclic structure is bigger, and there's only one branch hanging off of the cyclic structure. So we're going to give the carbon on the cyclic structure that has the branch attached the number 1, and then we can number the ring around the cyclic structure going up or going down. It does not matter, and we don't even really need to number it if we can see how many carbons we have there, but a lot of us can't see that, so we definitely have to number it. So we've got 8 carbons there. So our parent is going to be called what? With 8 carbons. If you said cyclooctane, you are correct. Cyclooctane. And that looks like a funny word because it looks like cyclooctane, but it's cyclooctane. Now, a common student mistake is to forget the cyclo portion when putting the full name together. So don't forget the cyclo. Now, looking at the branch, what we're going to do is put our carbons in there just so we can be sure that we've got 4 of them and not 5 of them. Now remember, my friends, you do not want to include the carbon that's part of the ring. So that red carbon on number 1, that is part of the ring, so it is not part of your branch. So our branch is this right here. And if you have a 4 carbon straight chain, what is that branch called? That would be butyl. And butyl comes from butane. All right, so what we have is we have 1 butyl cyclooctane, or you could just say butyl cyclooctane because that butyl group has to be on carbon number 1 of the cyclic structure because those are the rules. You make that carbon number 1. Alrighty, moving on to the next one. So how many carbons do we have in the cyclic structure? We have 1, 2, 3, 4, and again, I could number the ring around the other way. So where the number 4 is right now, I could have made that number 2 and gone the other way. So I have 4 carbons in this ring. And in the straight chain, I've got 1, 2, 3, 4 carbons. Oh no, they both have 4 carbons. So which one is the parent? Well, IUPAC says if you have a situation like this where the cyclic structure has the same number of carbons as the straight chain, the cyclic structure will take precedence for the parent chain designation. So our parent is going to be what? That is going to be cyclobutane. And our branch is going to be what? Our branch is going to be regular old butyl. Remember, butane turns into butyl when it is a branch. So we'll put that together, and what we will have is butyl cyclobutane. Now you could stick a 1 out on front, 1 hyphen to indicate that the butyl is on the first carbon of the cyclic structure, but you don't have to do that because you have a cyclic structure with 1 branch, and so it has to be attached to number 1. Alrighty, moving down to the chicken looking thing down there. What are we gonna do here? Well, we could number this structure a number of different ways. So we want to keep the combination of numbers the lowest it possibly can be, because that's IUPAC rules. So what I would do is 1, 2, 3, 4, 5, 6. That way we would have 1, 1, 2, 5. If you numbered a different way, say you wanted to do this, that would give you 1, 2, 2, 4. And you can see when we compare at our first point of difference, the 1 is going to win out because it's lower than 2. We can also do a different way. This is going to get kind of crowded in here. Maybe we wanted to do 1, 2, 3, 4, 5, 6, like that. That's going to give us 1, 3, 3, 4. And you can see that that's not going to work either, because this is giving us the lowest combination of numbers. Okay, so let's back up. Let's get rid of all the extra stuff we don't need. That's just clogging up our molecule there. Alrighty, so what we have is let's erase this up here just so we have some more room. Good, good. Okay, so we have 1-methyl, and we have a 1-methyl, and those two will give us 1,1-dimethyl. And then on number 2, what do we have? We have a straight chain with 3 carbons, and one of the end carbons is bonded to the cyclic structure. So that would be what? What's your guess? That would be propyl. And again, if you print out that one slide that shows you the most commonly used branches and you have it ready for you, sitting next to you as you work, that'll save you so much time. Okay, so we've got a 2-propyl, and then we have a 5-something. That's weird. That's that little snake tongue there. What is that, my friends? That is an isopropyl. So you can see that also has 3 carbons, but the connection point is at the center carbon. So that's not a regular propyl, that's an isopropyl. Alrighty, our parent chain, what do we have? It's a cyclic structure, so we're going to start it with cyclo, and it has 6 carbons. So that is hexane. And remember, don't forget the cyclo in the front. That is a common student mistake. Okay, we are going to assemble the name now. And this is the part that really bothers students, because we want to go 1, 2, 5, which would make sense to us, but no, we have to order them how? Alphabetically. And not only do we have to order them alphabetically, the branches, we have to ignore some prefixes and not ignore other prefixes. And if you remember from the last lesson, we said that if we have one of the Greek prefixes, blah, 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 blah. That must mean I need some coffee. If we have one of the Greek prefixes that's indicating a number, like di, tri, tetra, like number of branches, we're going to ignore that. So for dimethyl, we're going with the M. For propyl, that one's easy. We go with the P. And then for isopropyl, the iso is a prefix, but it is part of the name. You can't have isopropyl without having iso on the front, and that was one of the ones in the rules that we learned we do not ignore. So we're going to count the I portion of it. And that is definitely on one of the slides that we did. I suggest you print that one out also and have it handy for yourself. All right, and then we do A, B, C, D, E, F, G, H, I. Okay, that one comes first, even though the number 5 would seem like it would come after 1 and 2. We do 5 first. So we have 5 isopropyl hyphen, and then what comes next? M or P? M. So then we have 1, 1. And remember that between numbers we have commas, and between a number and a letter we have hyphens. So we have dimethyl. And then what? And then hyphen 2, hyphen propyl, no space, and then what? Cyclohexane. Whoo-wee! So, again, now you know why some of those chemical names seem so enormous, because you have to name everything that's there. All right, let's draw some. Drawing is so much fun. We want to do 2-cyclopropyl heptane. Okay, so heptane, how many carbons do you have in heptane? That's the weird one. That's one with 7. So let's go ahead and do the line bond structure. And remember, the first carbon happens when your pen hits the paper. So we have 1, 2, 3, 4, 5, 6. Oh my goodness, technology. No, 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 no. 1, 2, 3, 4, 5, 6, 7. There we go. Okay. So we have 7 carbons there, and if you need to check, that's good. That's actually recommended, just to make sure you've got your 7 carbons there. Okay, I'm going to erase those just for clarity here. So we've got heptane, not cycloheptane, just heptane. And on carbon number 2, we want cyclopropyl. So a propyl group is going to have 3 carbons, and cyclopropyl is going to draw 3 carbons in a cyclic structure, and what that looks like is which shape? A triangle. So we're going to go ahead and put that up there. So we have 2-cyclopropyl heptane. Now, could we have drawn our caterpillar upside down? Absolutely. So 1, 2, 3, 4, 5, 6, 7, and you can put your cyclopropane down like that, or you could have numbered your straight chain the other way, where you have carbon 1 here and carbon 2 here, and you could put it over there. Same with this one. If you would have numbered your chain backwards, you would have put your cyclopropyl group right there. When you're drawing it, you get to decide. C, draw T-butyl cyclopentane. All right, pentane has how many carbons? It has 5. And if you can't visualize what a cyclopentane looks like, think of the pentagon. Cyclopentane looks like a house. So we've got cyclopentane there, so we've drawn that, and then we have a T-butyl group hanging off of it. Now, again, we don't need to indicate that it's one T-butyl, because in a cyclic structure, if you just have one branch, wherever you put it, that's going to be considered the first carbon. Okay, so up here we had to put the 2 because we had a straight chain as our parent. If you didn't indicate where the cyclopropyl was located, we wouldn't know. All right, now T-butyl, that one's really easy. It just looks like a T, and you can put it anywhere on your cyclopentane. You can put it at the top, and then it looks like a Christian church, or you could put it on the bottom, one of the bottom carbons if you want. That's fine too. That's what T-butyl cyclopentane looks like. All right, D, we have 2-bromo, 1,1-dimethyl cyclobutane. Cyclobutane is fun to draw. Which shape is it? It is a square. Okay, so we've got a bromine on carbon 2 and we have 2 methyls on carbon 1. So again, you get to pick where you want to put your methyls, okay? Wherever you stick your methyls, that's going to be carbon 1 and then we'll work from there. So you can do one of the top carbons, which is usually what students do, or you can decide to be different and put your methyls down there. Now, because you did that, that is definitely carbon number 1. So you can just draw sticks like that, or you can put CH3 on the end. Now, carbon number 2, you can either go up or you can go to the right. Just pick a direction. You just don't want to put bromine diagonal across over on the top right. That would be wrong. Okay, so let's go up, and that means we would go ahead and put a bromine here. Let's get that better. You can also draw the bromine out to the left if you want. That's fine. What we need to remember is there's also something else bonded to carbon number 2 there, because carbons need to have 4 single bonds. What else is bonded to the carbon there that we don't see, that we assume you know is there? If you said hydrogen, you would be correct. Now, you can leave the hydrogen not drawn there. That is preferable. Then you don't have to worry about getting it right. So let's go ahead and remove that. Okay. So we would probably want to clean this up just a little bit like that. And then you have 2-bromo, 1,1-dimethyl-cyclobutane. And that concludes this lecture because the next slide is blank. Yay! All right. Bye-bye.